like organizing the Academy Awards with no dry run. Thank you all so much for coming. It's my very great pleasure to welcome you to the 24th Goldschmidt here in Sacramento. My name is Barbara Sherwood-Lawler. I'm from the University of Toronto, and I am the current president of the Geochemical Society. And with me today to assist in these awards is my colleague, president of the EAG, Christopher Ballantyne. It's our very great pleasure to start today's proceedings first and foremost with the awarding of the Geochemical Fellows. In 1996, the Geochemical Society and the European Association of Geochemistry established the honorary title of Geochemistry Fellow. This was to be bestowed on outstanding scientists who have, over a number of years, made a major contribution to the field of geochemistry. Recipients of the Urey Medal, of the Goldschmidt Medal, and the Tribes Medal are also honored as Geochemical Fellows. And starting this year, both societies agreed that the recipients of the other medals as well, the Geochemical Society's Patterson Award and the EAG's Science Innovation Awards, would also be honored as Geochemical Fellows. So we have quite a large number today, many of whom are here to join us. What we'll do in this ceremony is introduce each by name and ask each of you to please step forward. We'll have a very short awarding of the certificate and photograph with each individually, and then ask you to please gather at the bottom of the stairs for a group photograph as well after all of the Geochemical Fellows have been introduced. I'd like to remind you as well that this will be followed right afterwards by our first plenary, Dr. Pamela Conrad, and so I'll be doing an introduction of that at the end of the brief Fellows Award ceremony that we're holding right now. Great. With that then, I'll start by announcing the 2014 Geochemical Fellows. There are a number who are actually absent today and were not able to join us, but we'll start with them first. Again, congratulating Dr. Yuri Amelin from Australian National University, again, not able to join us today. Dr. Richard Arkelis, also from Australian National University. Dr. Shan Gao of the China University of Geosciences. Dr. Bob Hazen of Carnegie Institute for Science. And Dr. Hiroki Nagahara of the University of Tokyo, who hoped to be here, but we believe has been delayed due to a flight delay. So congratulations to all of those in absentia. And then I would like to start with those who are here and ask Mark Hirschman from the University of Minnesota to please step forward. Dr. Becky Lang from the University of Michigan. Dr. Bernard Marty from the Centre de Recherche Pétrographique et Géochimique. We've lost Bernard. We'll get that to him later because I know he is here. Dr. Martin Palmer from the University of Southampton. Dr. Adina Payton from the University of California, Santa Cruz.
Thank you.
In addition, this year we have some extra awards as we, when the decision was made to make the Patterson and other fellows the awards, the Science Innovation Awards as well, this meant that there were some past recipients of those prizes that we wanted to honor with the same distinction of geochemical fellows. And so as Patterson medalists, previous Patterson medalists who are being honored today as new geochemical fellows, once again, we have a number who were not able to join us, so we would like to congratulate in absentia Dr. Ken Brulin, Dr. George Luther, Dr. Chris Reddy, Dr. Stefan Schuten, Dr. Jeffrey Severinghouse, and Dr. William Sunda. Joining us to accept their awards today are Bob Anderson of Columbia University, Dr. Larry Edwards from the University of Minnesota, and Dr. Bill Fitzgerald from the University of Connecticut. Hiroko has arrived. Wonderful. Perfect timing. So join me in congratulating Dr. Hiroko Nagahara of University of Tokyo. And then finally, two additional names in absentia. These are winners of past EAG Science Innovation Medals who are being honored today as new geochemical fellows. Dr. Kai Hirose from the Tokyo Institute of Technology and Dr. Danny Sigmund from Princeton. So again, if you can join me in congratulating all of today's recipients. And now for the main event. It was my very great pleasure to welcome you to the first plenary lecture given today by Dr. Pamela Conrad. Pan is a mineralogist and astrobiologist working at NASA Goddard Space Flight Center in Maryland. Her research focus is on understanding planetary habitability and the development of approaches for measurements both on environments on Earth and also on other planets, most especially on Mars. She is the Deputy Principal Investigator and Payload Investigation Scientist for the Sample Analysis on Mars Suite, otherwise, of course, known as the SAM instruments, part of the Mars Science Laboratory Science Payload, presently exploring Gale Crater on Mars on the Curiosity rover. And we're deeply grateful to her for making time in an incredibly busy schedule. Not just the busiest person on this planet, one of the busiest persons on two planets, Dr. Pan Conrad.
This is one of my favorite topics, and the more I learn about it, the more I scratch my head and realize I still don't know enough. And so I'm hoping that you can join me in this pursuit and maybe fill in some of the holes about which I wonder late into the night. I've got my email address on the front slide because sadly I have to leave right after this talk. So if we don't get to your question, please write me and I'll do the best I can. Usually you acknowledge all of your colleagues at the end. This time I want to do it right up front. I'm very honored to be here to give this talk, and I couldn't do it without the more than 450 colleagues that are helping to explore the habitability of Mars every day now, the many, many others before us, and also those people who have accompanied me into the field schlepping God knows how many instruments up and down volcanoes. So I'm going to get right on with it and try to do this with some alacrity so that we can get to the juicy stuff, and that's your questions. First of all, this is a place where we recently spent a little bit of time in Gale Crater. It's called Kimberley. If you just look at the face of it, you see a pretty barren environment. One of the differences between trying to characterize the neighborhood and trying to look for biosignatures is that there are just so many aspects to what makes an environment potentially habitable. There's a big difference between trying to understand the present habitability of an environment and what it might have been in the past, because of all the processes that affect the stratigraphic record as you probe it. So I hope what we'll do is raise some questions about what we're looking at in the present time and how they might have changed through deposition and alteration in the stratigraphic record, and what that portends for our ability to try to assess the habitability potential of past environments, not just on our planet, but also on Mars. I'm going to start by talking about two completely different aspects of habitability potential. They're both important, and I kind of see them both as really those factors that enable the chemical potential of an environment, because after all, taking up a living and conducting the business of metabolism is really about chemistry. And we tend to talk about habitability assessment with respect to the chemical requirements for life, which are based loosely, and I have to say loosely because sometimes we adhere to them with some catholicity, on the requirements for earthly life. So, for example, when we search for other planets in our solar system and try to invest our ability to assess the habitability potential, we look for water, because all of the life here requires water. Indeed, when we look beyond our solar system and we look for exoplanets, we're also looking for signs of water. So we already know that we have a chemical requirement that we've put at the top of our list. Obviously, there are chemical elements that we think are important. The subset that we all learn about: carbon, hydrogen, oxygen, nitrogen, sulfur, phosphorus, a whole bunch of other traces, some more abundant than others, and some over time have become less or more important to Earth organisms. We have no clue what life on Mars might utilize, if it has ever arisen, so we have to keep a rather open mind and use benchmarks. We also know that in addition to the chemical requirements for life, there are physical requirements. And while we pretend that once we have found the chemical requirements, that's it, it's not it. And we know, for example, that there are thermal requirements. So we can't be too hot, we can't be too cold. And we also know from studying microbial life on Earth that this range has kind of stretched over time, and we find new life that's more tolerant of hot and more tolerant of cold, and in fact, in the extremophile literature, more tolerant of a host of environmental factors. But there are other things that turn out to be important as well. It's probably no surprise that ionizing radiation is a potential showstopper in many respects. One thing we don't know is whether or not there's a minimal requirement for ionizing radiation for any type of life. We might speculate on that. The size of a planet is a big player in determining how it off-gasses, how its surface evolves relative to its interior. Does it fractionate? Does it not? And also its relationship to the other bodies. So size for the planet makes a big difference, and also size of objects either captured or formed from, such as our moon, our best friend forever, which has stabilized our rotation. And ultimately, as we transfer our angular momentum to the moon will get further away, our days will become even longer, and we won't be here to enjoy what the life that has evolved from us does with that little geophysical trick. The dynamics of an environment also play a role. If you're an organism and you live under a place where rocks are falling down on you, you're going to die. Those kinds of things are obvious, but if you think about environmental dynamics in other respects, we humans are pretty good at building homes where the mountain occasionally falls down, slides down. We're on coastal areas that are periodically inundated with floods and storms. So organisms push the envelope looking for fresh habitat, and sometimes the environmental dynamics decide otherwise and they leave. So in trying to assess this in present conditions on Mars, it's a little bit easier. Trying to figure out what the environmental dynamics might have been in the past are a little bit harder. You can look for rock types that are indicative of a highly dynamic environment, but there are other factors too. You can't just base everything upon whether or not water was flowing quickly. So that's an important factor. The late heavy bombardment, it was a bad time to be alive if you had started already. That's another type of dynamic. So from the very micro scale to the very macro scale, how often things change and how dramatically they do so, this can be an important player in the habitability potential of an environment. So I'm going to summarize this up very simplistically because I've only had a couple of hours of sleep, and tonight I'll get even less. You've got to have the right stuff. You have to have the right conditions for that stuff to chemically react, and it's all got to be together at the right time. The right time for having all the materials together in the given environment that could be habitable, and also the right time during the evolutionary track of the candidate environment. Sometimes these factors change at different rates from one another. So what gets tricky in trying to probe this on Mars is you've got to come up with a different sampling rate to examine each one of them. So keep that in mind. How we measure the chemical environment of a rock, the mineralogical environment of a rock, and the present air temperature, ground temperature, wind speed, wind direction, and so forth, those all have to be done on a different cadence. If you want to do this in situ on another planet, it becomes even more difficult because there are lots of competing needs, and then you have technical constraints, human resource constraints, and of course, the ubiquitous cost constraints. In the rock record, we often are confounded by what the evidence is for habitability potential as distinct for the evidence of diagenesis. These are very tricky, especially if you're looking at sedimentary environments where you have clastic deposition and you don't know what kind of weathering environment the original clasts were faced with. So all of these things come into play, and they've all confounded us in the past, the present, and probably will in the future on Mars. And I think that if we're fortunate enough to begin in situ habitability assessment on other planets, they'll confound us there as well. I've got this laundry list of potential factors that I think could affect habitability. In some environments, some are more primary than others. I've argued with some of my colleagues about this. I've been told more than once, well, all you need is the right chemicals, just add water and mix, and you should get life. And sometimes you don't. So I have to confess that I really don't know what the comprehensive list of these factors might be. But I think that if we measure as many things as we can think of as often as we can, we might begin to see associations, especially if we do this on Earth and see what kind of life is associated with what collection of habitability attributes. Only then might we be able to get to some sort of predictive tool. So when I think about those things that might be biosignatures, I think of them as distinct from those things that might be habitability signatures. Let me give you an example. We look at stable isotope ratios in the atmosphere of Mars, in the rock record, and some of these stable isotopes on Earth have given us clues about whether or not processes have been biologically mediated or not. For example, carbon, we all know to look for isotopically light carbon, and then we blame it on life. The problem with using isotopic signatures as an environmental requirement for habitability is that right now we can't think of anything except for one element for which there is an isotopic requirement for habitability. That one thing is hydrogen. Hydrogen, when you get the heavier version of it, is twice the mass of the light version, so that's a showstopper for life on Earth. Too much heavy hydrogen and you can't use it anymore. So that's something to think about on another planet. It could be that it is important in a second order manner to understand the isotopic ratios of materials to tell us something about the processes that have affected the environment. But as such, we're going to leave stable isotope ratios off the list of potential chemical requirements for habitable environments. So the arc of history bends toward mobility. We find that as we have moved from the Viking mission, which was pretty spectacular, 2 spacecraft launched a month apart, 2 different places that measured quite an array of habitability attributes on Mars, we decided to begin exploring mobility. Exploring the use of mobility is very important just because it gives us a broader array of samples. A broader array of samples, we're more statistically representative, but then as you expand your ability to roam further, you also have to expand your ability to sample more, conduct more experiments, do more things with the ground. So as you can see, the rover to the right of the screen is a pretty big one with respect to the little tiny Pathfinder that's all the way to the left. That one was about as big as a shoebox, and Curiosity is about as big as a Jeep. The Viking missions, which did return ambiguous results in the minds of some, have returned some pretty conclusive results in the minds of others. We still debate the meaning of the Viking biology experiment results. But one thing that we can say about Viking is it set the stage for our approach to habitability assessment now. Viking was looking for signs of life. Curiosity is not specifically looking for signs of life. It's looking to characterize an environment. Would we take it if we found signs of life? Of course we would. But the problem is, again, we only have life as we know it on Earth to go by. So what we do know is that throughout the observable universe, we can count on the periodic table of the elements, and we can count on thermodynamics and understand what minerals will form under what conditions. And so those kinds of measurable things that we know we understand give us a bunch of things we can put to the side if we find chemistry we don't understand. Trying to understand the chemical potential of an environment doesn't mean the same thing as looking to find evidence of life, because what we're really after when we're looking for organic molecules on another planet is to understand whether or not you can conduct that kind of chemistry. Can you do covalent chemistry? Can you do anything other than make ionic crystalline solids? So Viking was very, very much in the same approach as we have been with Curiosity. And I'm going to come back to Viking in a minute. The MSL mission goals, as I have already told you, are primarily to assess the habitability of Mars by looking at processes, trying to understand what processes have affected the surface, what's happened with water there, what is the radiation environment like, and so forth. These measurements are very well suited to understanding the habitability potential of organisms on Earth. So as such, they're a really good model for understanding the habitability potential of Mars, not because we expect Martian organisms, should they exist, to behave exactly as we do, but because we think we can understand that there'll be the same chemical and physical challenges to chemistry. And life, once again, is chemistry. The payload that we have, the tools that we use to address the questions that we have, is actually able to answer almost everything on my laundry list of chemical and physical measurements that I would do to try to understand whether an environment is habitable. These instruments have been working like a charm. We've been on Mars almost 2 years now. We're just about a few weeks shy of a Martian year. We have 17 cameras. They all do slightly different things. We have chemical instruments. We have environmental instruments. I'm not going to go through the payload blow by blow because at this late date in the mission, I think you're all at least familiar enough with it that you know which website to go to if you've got a more specific question. My instrument that I work on is a measurement that measures volatile elements. If they're not volatile when they get to us, we try to change them into something volatile. More about that in a second. Our field site, equatorial, just 4 degrees south of the equator. Gale Crater is a very large impact crater. As you can see here, it's 154 kilometers across. We are not going to be exploring all 154 of them. We chose this site because the central mound has a very thick layering of sediments. You can probably see it a little better in this cartoon where we have a cutout of these sediments. Our thought was that if we could get to the central mound and ascend, we might get a better look at lots and lots and lots of different geological materials and get some idea of the diversity of Mars. The chemistry measurements that we've done have been an orchestrated effort between the alpha particle X-ray spectrometer and the ChemChem, which is a laser-induced breakdown spectrometer, to get elemental chemistry. These things work together. The APXS instrument has a larger footprint, and it integrates over a longer time. The laser, for the laser-induced breakdown spectrometer, can zap rocks here and there and also do some depth profiling. What's important about having these instruments, it means we can rapidly assess the chemical elements associated with particular targets so that we can decide which targets are the most promising and narrow down our search space before we go into the really very energy-intensive activities of taking contact measurements, putting a drill down, getting powdered drilled material and putting it into the ChemIn X-ray diffractometer and the SAM mass spectrometer suite. What we think that we can do with our dynamic albedo of neutrons experiment is get an idea of what water is beneath our rover. And really what we're measuring is hydrogen as a proxy for water and chlorine. And Dan has been operating religiously since we landed and giving us a pretty good idea where the water content lies in abundance and what kind of correlations we can make with the other instruments, the APXS, the ChemChem, and the SAM measurements. When SAM ingests solid materials, it pyrolyzes them, and we can see the light elements as they evolve during pyrolysis. We do have a chemical separation and processing laboratory inside of us. We haven't used that yet. And we've also got the capability to directly inhale volatiles as they exist in the Martian atmosphere. Some of the chemistry that we have measured so far has enabled us to do some things that we didn't start out planning to do, including some radiogenic age dating and some exposure age dating, and I'll talk more about that as we get to the end. I want to make sure I don't go over. The sample analysis at Mars instrument is actually a mass spectrometer, a gas chromatograph, and 2 different tunable laser spectrometers, one of which can be tuned to look at both CO2 and water. Again, this stuff is freely available information. I'm not going to go into specifically the nuts and bolts of SAM, except to say that the arc of history not only bends towards justice and mobility, it also bends toward complexity. And in case you want to build your own, here's the gas flow diagram. Good luck. I've been working on this thing for 10 years, and I finally now can close my eyes and remember where some of the 53 valves are. So volatile chemistry of the atmosphere is important with respect to habitability assessment for a couple of reasons. Obviously, we've all known for a long time that we have a measurement from Viking, not a measurement, but we have measurements from Viking that then have worked together in concert with meteorite measurements that give us an idea of the major gases in the Martian atmosphere and their mixing ratios. So SAM has measured those things too and confirmed the theories that we have atmospheric losses. No surprise there. We have slightly different abundances of argon and nitrogen, which we're still trying to understand, try to get a handle on whether that's a recent phenomenon or differences in measurement. And we've made stable isotope measurements on the solid materials as well as the atmosphere because we're able to conduct some of the pyrolyzed gases from our oven, not only into our quadrupole mass spectrometer, but also into our tunable laser spectrometer. Not a lot of surprises there either. What is really interesting as we have looked at the volatile chemistry is we do see some organic molecules. Some of them are some of the organic molecules that Viking saw. Viking had a particular explanation for it. We're not sure of what the explanation is. It could be that we have leaked a little bit of the derivatization fluid that we use in our chemical processing laboratory, affectionately known as MTBS-TFA. I'm not an organic chemist. I couldn't begin to recite the name of that molecule. But some of it could also be Martian, indigenously Martian. We're working on it. We don't have an answer for you yet. Excuse me. I'm going to skip this because we already talked about this. So one potential explanation for why we're having such confounding results with regards to organic chemistry on Mars was postulated by Steve Benner in a PNAS article in 2000. Steve basically postulated that through photolytic breakdown processes, you could get stable molecules that don't volatilize easily, and that maleic acid and the like, benzene hexacarboxylates might be species that we would see, but they would be difficult to derivatize and get into SAM. Thanks a lot. See, this is what happens when you yak too much. So a potential explanation for why we're having trouble deciding whether or not we see organic molecules is that they're there, but they've become diagenetically altered into something that we can't see in our type of instrument. Time will tell. We don't know the definitive answer to that yet. What we've done is not only pyrolysis experiments, but we've also done some combustion experiments. Now we have this other problem on Mars, and it's not a new problem. We've known for a long time there was some kind of a oxidant on Mars. Phoenix, in Mike Hecht's paper in 2009, found evidence of perchlorate. We see evidence of perchlorate as well. So we could be potentially dealing with a Clorox planet. That could be one explanation for the chloromethane and the dichloromethane that Viking saw and that we see. We don't know. There are some differences in how Viking operated and how SAM operates that would allow us to get a wider array of samples. So, for example, if the theory is that this oxidant is in the dust or in the soil, theoretically, we should learn different when we drill into the rock. We also see these types of phases when we drill into the rock. So there's a lot of oxidant stuff. Now, whether or not that oxidant stuff has been in the top layer and then has formed sedimentary rock, and that's why it's in the rock, is it ubiquitous at some depth in the crust? We don't know. We do know from the meteorite work, from the Filiberto and Treman paper in 2009, that there's more abundant chlorine than water in the mantle. But how that chlorine is distributed between the interior of the planet and the exterior of the planet makes a big difference in how available that chlorine is to oxidize other phases that sit on the surface. So it's very confusing. So even though we can do more samples than Viking, and we can roam around, and we can get inside the rocks, and we can do wet chemistry, still don't have a definitive answer yet. So if we can do organic chemistry on Mars, it has to wait until we get more data. We're still working. The evolved gas analysis has shown us that there are enough light elements inside the rocks and in the dust. On the left, you see what we found in a wind drift called rock nest. And on the right, you see the first drilled rock on Mars. And you see things like SO2, HCl, you even see some nitrogen compounds, not a lot. You see water, you see oxygen release consistent with perchlorate. So we haven't looked at that many rocks yet, and we hope to look at more, and we're trying to pick up the beat as we get closer and closer to Mount Sharp, when there will be many more layers closer together, and we should be able to get more diversity. Let me skip quickly to physics. I already told you that that's an important component. So we're measuring the physics in terms of things like temperature, air pressure, wind speed, wind direction, relative humidity, radiation. We do this at a regular cadence every hour, and then sometimes we do extended observations. We see a wide thermal swing, about 90 degrees between day and night, but it's not a showstopper based upon organisms that are thermally stable on Earth. The pressure measurements are really interesting. This is important because you can see when you measure the radiation, a perfect diametrically opposed, gorgeous example of phase canceling. The radiation is higher when the atmospheric pressure is lower, and so here is definitive proof that even with the tenuous Martian atmosphere that we presently have, you still get some manner of protection against the attack of ionizing radiation. If the atmosphere escaped late, then you had protection for a long time. If it escaped early, you had less protection, not only for putative biosphere, but also less protection to preserve against diagenetic alteration, photolytic degradation of potential habitability signatures, if not biosignatures, in the stratigraphic record. So this radiation and pressure calibration of one another is extremely important. The physical properties of the rocks also go to the micro scale, just to go from the sublime radiation and pressure measurements in the atmosphere to the ridiculous. I'm pulling in now some of my Earth data. The reason why you can have rocks like the Beacon Sandstone at Battleship Promontory in the dry valleys of Antarctica hold so many organisms is because you have these beautiful holes in between the grains. Basically, the porosity is a key determinant in how much biomass you can hold in the rock, and also how fast the materials diffuse away so that you can bring in nutrients and get rid of waste products. So porosity, permeability are important physical properties that are part of the rock characteristics that would be geological habitability attributes as well. As we go to the geological stuff, some of the most important things that we can look at are the mineral component of the materials in the Martian crust. We haven't had the opportunity to look at too many samples yet, but what is really interesting from the samples that the ChemIn analysis has done, and here I've got some data from Dave Anneman's paper, the science paper that was published late last year. We've got a lot of basaltic-looking stuff. This is not incredibly diverse the way Earth is incredibly diverse. The caveat here is we haven't looked at that many samples yet. But what we can say is that what we see here is not stunning in its mineralogical diversity. So that tells you something about the processes that have altered the rocks that we have looked at. If you look at the morphology and texture using our cameras, you see more evidence of processes that have affected the environment. If you look in that hole, I don't know if you can see this in this kind of lighting, but there's a little white vein there. I don't know if you can make that out. So that's more proof that you've got alteration. Beyond that, you can see things like evidence for an ancient stream bed that was published by Becky Williams in the conglomerates that we saw. And what you see is lots of evidence for sedimentary deposition in water. That's not a surprise. We expected that from some of the orbital data that we had from the Mars Reconnaissance Orbiter before we landed. If you start looking more at morphology and texture, you get a better sense of populations of grain sizes, types, and shapes. And we're able to do that with the MALI, the hand lens imager from Malin Space Sciences, for which Ken Edgett is the PI. So we drilled our holes and we looked at sedimentary rocks. And what we found is a mudstone, and we published this in the Grotzinger et al. Paper in 2013 that characterized this Yellowknife Bay environment as a past environment that was potentially habitable on the basis of its chemistry, its mineralogy, and the geologic story that made it look like a fairly benign paleolacustrine environment. What was the physical environment at that time? Was it after there had been substantial atmospheric loss? What was the radiation like? What was the wind like? There are lots of physical things we don't know about that. So let's skip ahead to preservation of organics in the near surface. We think that there's a high enough flux of ionizing radiation that it's going to be tough to find a robust diversity of organic molecules. I already flashed the Steve Benner PNAS paper, but beyond that, Alex Pavlov in our lab, who has put in this 2012 paper and also another recent paper in 2013, more modeling about the size and type of molecules that might be robust to ionizing radiation and to what depth and for how many years on Mars. So to cut to the chase about how organics might be affected, there are, of course, a number of factors which might enhance or facilitate rapid degradation as opposed to preservation. But one thing that we do know is that if you have a reservoir of organic molecules from the past and they were buried right away, they may be safer than anything very close to the surface. Our drill only goes down 5 centimeters. So the question is, how do we get to stuff that's been buried and protected for a long time? It's this preservation potential thing which could confound our ability to assess the habitability potential because of the surface environment being so subject to photolytic degradation by ionizing radiation. So what we've been thinking about is, how do we tell how long something's been exposed? So the amazing Ken Farley came up with an idea which he proposed as a participating scientist at MSL, to use the SAM instrument in a way that we hadn't thought we'd be able to do. And his technique was to use the APXS instrument that measures how much potassium is in a given target, and then use radiogenic argon-argon dating, and also try to do exposure age dating using correlative sets of elements, looking not only at argon, but also at helium and neon as well. And I'm sort of cutting to the chase here. His experiment worked beautifully, and he published this paper also in Science in late 2012. We found the rocks are old, 4.2 billion. Of course, there's a big error bar, but it's pretty good. It's the first age dating experiment on another planet. And we're very happy that the age wasn't older than the planet, because at least that means the technique isn't caca. We also found an exposure age that was pretty young, an average of about 78 million. So we feel very good about this experiment, and we think that this experiment will help us to predict which rocks might have the most conducive exposure age to being able to have the best preservation potential for organic phases. Once again, not because we're looking for biosignatures, but because we just want to know, can you do that chemistry? So our strategy is to look for organics in rapidly eroding faces, such as scarp faces that show morphological evidence of rapid abrasion, different types of textures, that lineations, and those types of morphological features that would help us predict that that might be a promising candidate. Then to date those, and then look for, of course, evolved gases and see whether we see a different complement of organic materials than what we have seen so far, for which the genesis is uncertain. So I think it's time to try to rapidly pull this together and get to your questions. We know that there was lots of good chemical stuff in Mars once. We've already analyzed that at Yellowknife Bay. The question is, was it at the right time? Was the place habitable? So here's the thing. We found the chemistry there. We also have dated it, and the rocks turn out to be really old. So do those rocks mean that it was a potentially habitable environment if it was really old, like before the atmosphere went away, after the atmosphere went away? We don't know. So we have to look at more rocks. And we're on the way to do so. We're heading up toward Mount Sharp even as we speak. Today, we're on the road. It's Sol 654. We're driving, and Mount Sharp awaits us. So whether or not we will ever know definitively if we have habitability on Mars in the present and in the past is probably not going to be answered by MSL, because MSL is in one crater in one spot. But if we take together all of the data from Curiosity, all of the data from the past missions, eagerly await the arrival of ExoMars, and then looking forward beyond ExoMars to the 2020 mission that is supposed to collect and cache samples, perhaps then we'll have enough data to enable us to assess the habitability potential of Mars. The state of the art is evolving every day, and I might have a different answer for you tomorrow than I have for you today, but I'm not going to conclude anything yet, and I'll take your vote and your questions now. So, Barbara, we started this a little bit late. I'm not sure how many questions. All right. So I can see nothing, so you'll just have to shout them out.
Pan, over here is Steve Ruff from ASU. Regarding the age date, 4.2, this is a sedimentary rock, so you're dating the detrital material, presumably, and you don't actually know the age of the emplacement of the sheepbed rock, correct?
That's absolutely right. That it? No questions about silicon-based life or anything?
Hi, thank you very much for the talk. It's wonderful. I have a question about the oxidants. You mentioned perchlorate. You found that on Mars. I just wonder if you have any conclusion or information about how that relates to the gypsum, the oxidized forms of minerals, or is still under investigation? Just curious. Thank you.
Sure, that's a great question. So, what you'd like to see is a whole bunch of scale, a binary from very reduced stuff to very oxidized stuff. We see tantalizing hints that we have had more neutral or reducing conditions from the chemical evidence in the sheepbed rocks that we analyzed. But we don't know if the same events oxidize the rocks that are highly oxidized, or whether they continue to re-react and oxidize each other, what the different events are, or whether there's more than one oxidant. There's certainly no definitive answer to what the complete complement of oxidizing materials are. We know there's chlorine there. We know there's bromine there. We know that there is actually probably more chlorine phases, which we're calling oxychloride phases, but we don't know what all of them are yet because we haven't looked at enough samples yet. So we do know that our work is confounded by the problem that when we heat up materials in our pyrolysis oven and perchlorate is there, the reaction between the perchlorate and water and other things there can alter phases. So this is a variable that we're going to have to work on hard.
Thank you for coming. I have a question about the age at which the atmosphere may have been removed. Has it been established? If so, how? And if not, how would it be established one day?
Wow, what a great question. The short answer is that it hasn't been definitively established. The theory is that during the late heavy bombardment, Mars lost its magnetic dynamo and then was unable to shield itself against the solar wind and cosmic rays, and that is dated somewhere between 4.1 and 3.9 billion. But whether or not we can pinpoint the loss of the atmosphere on Mars, I don't even know the answer to that. Obviously, you get corroborative information from meteorite literature, dating of meteorites, and looking at the phases that trap atmosphere. We don't necessarily have the same phases that trap the atmosphere, which are minerals with closure that can be radiogenically dated. So some of the people here are much more expert than I am about what it would take to be able to definitively pin that down.
Perhaps using some of the recent lava flows and looking at magnetic orientation, you could find where that magnetic orientation disappeared and simply date the closing temperature of the lava.
You know, that would be great if we could A, find a lava flow, and B, if we had enough remnant magnetism that we could tell that. We don't have a magnetometer on Mars Science Laboratory. Perhaps if you would like to propose a discovery or a scout, I think it's a great idea. The other thing about that is, if you are trying to draw a parallel between how we do this on Earth and how we do this on Mars, we wouldn't necessarily know what is a recent lava flow unless we dated it. So we're back to this chicken and egg problem of dating something and then discovering whether or not it has remnant magnetism, and whether it's remnant magnetism or planetary scale evidence of the geodynamo that is no longer there. So since that is thought to have disappeared a long time ago, it would not be associated with a recent flow. So I'm not exactly sure how to do it, but probably somebody who does this is better equipped to answer this than I am.
Pan, up here. This is Liana asking a question about your perchlorate. Wouldn't it just kill everything?
You mean things that were actually alive, Liana?
Let's assume, for the sake of the argument.
That's why I like to call it the Clorox planet, because I think, yes, it would, but if you're distributed only on the surface, and you can get beneath that, then I think it wouldn't be as much of a problem. The question is, do you have chlorine in some other reactive phase that's more reduced beneath the surface, and if so, at what depth? So I'm uncertain.
Thank you.
And I can't see where you are because these lights are bright.
Okay, so I also have another question. Thanks for your talk, first of all. And I would like to ask, under terrestrial conditions, we know that fatty acids may be preserved even in fossilized organic material, being a direct indicator for life. Would you think that under like circumstances like in old riverbeds or something where like fossilization might have happened, that would you think that you could find, like, if they were based on the same principles, that you would find such like molecules also on Mars? Or are you looking for them? Could you detect them?
Well, certainly my colleague Jennifer Eigenbrod would love to find fatty acids. We haven't found any yet. The question is what their robustness is under photolytic degradation of not only background galactic cosmic rays, but also solar energetic particles, and so how old they are and so forth. So we're open to any and all classes of compounds, molecules, and minerals that will inform us about the diversity of chemistry that we can do on the Martian surface. Awesome.
Please join me in thanking Pamela Conrad once again for the wonderful opening ceremony. Thank you so much.
My pleasure.
And please remember to join us for tomorrow's plenary as well, where we will have the guest lecture and some of the GS medal ceremonies. Thank you.